We're going to look at vectors now, and first and foremost, I'd like to say that a vector is an arrow. Nothing less, nothing more. It has a length, and it has a direction in which it points. The length is also referred to as the magnitude. And in the case of the xy coordinate system, the direction is given by an angle theta with respect to the positive x-axis. If the tip of the vector is the point in the xy plane, say AB, then the vector itself, I'll call the vector A, is equal to, we use angle brackets, A comma B. It looks like an ordered pair. I mean, it is an ordered pair, but we have angle brackets instead of parentheses to distinguish it from the point in the xy plane, which has coordinates AB. So A and B are coordinates of a point when we write them with the parentheses, but they are components of a vector when we write them with the angle bracket notation. Now there exists a vector called the zero vector. It has components 0, 0, or in the case of in R3, in 3 space, 3 dimensions, 0, 0, 0. The zero vector has a magnitude of 0 and actually no direction. So the statement is actually every non-zero vector has a magnitude and a direction. So aside from the zero vector, every vector has a magnitude and a direction. As I just said, we see here that I wrote the A vector with a little arrow over the top of it, and that's how I know that it is a vector and not a real number. The same is true of the zero vector. I can write it as a 0 with a little arrow over it, and that just indicates it's the vector 0, not the number 0. How many components it will have, whether it's in 2 space or 3 space or 8 or 9 space, well, it wouldn't be space. It may be an 8 or 9 dimensional vector. That's going to be inferred from context. Now, you've seen vectors before, more than likely, and oftentimes they'll represent like a velocity or a force or something along those lines. And that'll be true if it can be true if we have, like, 2 components were in 2 dimensions, or 3 components were in 3 dimensions. These can represent physical. They can have physical attributes. They represent physical situations. If we have something that's in higher than 3 dimensions, say 4 or 8 or 10 dimensions, then it's simply the case that the vector doesn't have a physical application. It could be that in the case of a vector that's got 5 dimensions, so A1, A2, A3, A4, A5 are components of the vector, this could be part of a business model where each of the components could represent the cost of a different item or a different piece of material, like raw materials or something. So we can absolutely have vectors that are in higher dimensions than 3. They just don't have a physical meaning. In our work, we're going to be mostly limited, almost exclusively limited to 2 and 3 dimensional vectors. Now, I kind of ended this sentence here saying every vector has magnitude and direction, but I actually wasn't done yet. They do have a magnitude and direction, but not a position. And I will show you what I mean by that. Suppose I have here a vector A that starts at the origin and points out above the first quadrant, and I've shown you what is called the trace in the xy plane. And then I have this other vector which has the same length as A and then points in the same direction as A, but has a different starting point. This would simply be a copy of A. For all intents and purposes, they are the same vector. So this is what is meant by saying they have a magnitude and a direction, but no position. The magnitude and direction defines the vector. It doesn't matter where that is. We can move this vector wherever we want, and it is still a copy. Well, I didn't take the arrow with me. It is still a copy of A, no matter where I put it. So now let's say over here, these are traces in the xy plane. One for A, one for the copy of A. And you can see here I'm indicating that this is oriented in a different position from A. Now for some vocabulary here, A has a tail or an initial point. And it's the end of the vector that doesn't have the arrow. The end of the vector that does have the arrow is called the head or the terminal point. Now let's turn to the copy of A, and let's suppose that the copy of A has an initial point of P, which is going to be given by x1, y1, z1. And then the head of the copy of A has a terminal point, or the head is Q, or the terminal point is Q. It's not that the head has a terminal point. Anyway, the coordinates of Q would be x2, y2, z2. Then what we can say is A is represented using angle brackets as x2 minus x1, comma, y2 minus y1, comma, z2 minus z1, where, and then end with the angle brackets, where the components of A are the differences in the coordinates between Q and P. And for this, order absolutely matters. And we have the terminal point coordinates minus the initial point coordinates. If we were to reverse the order of those, we would end up with a vector that points in the opposite direction, which would then not be A. So just to recap, any vector that goes from P to Q, we're going to form some differences. We're going to subtract the coordinates of P from the coordinates of Q. The terminal point comes first. It's terminal minus initial. Now, if the tail of a vector is at the origin, as in the case of A, then the vector is said to be in standard position, or is said to be a position vector. And so here A is the position vector, or is a position vector. The copy of A is not, but it's the same vector.